Okay, dear friends, Maths Aspirants is a community of math lovers, maths research scholars, students from different parts of India, started by myself in the year 2017, and we used to conduct several online problem solving sessions to help the students who prepare for different competitive examinations. As a part of that series, today we have a session on infinite series, and we have Miss Nandana K Vasudevan is with us to engage the session on infinite series. Ms. Nandana is currently pursuing Ph.D. at Amrita Vidyapeetham, Coimbatore. I express my gratitude to Nandana for being with us, and I hope that today's session will be really a fruitful session to all the participants. I welcome everyone to this event. Welcome, Nandana.
Thank you, sir. Good evening, all. So today's session is regarding infinite series. We have already completed a session in sequences of real numbers. In that, we have discussed the definition of sequence, then convergence of sequence. Apart from convergence, we have seen oscillation, divergence, and certain theorems and all which are used to check the convergence of a given sequence. So today we are mainly focused on infinite series, which comes along with sequences. So we begin with the definition of infinite series. So in order to define a series, we should be given a sequence. Okay, that is, if Xn is the sequence in R, then the infinite series or simply series, which is generated by that sequence, is the sum of all the terms in that sequence. And it is denoted by sum n equals 1 to infinity xn or simply sum xn. And relating to every series, we can find a sequence called the sequence of partial sum. And how we define this partial sum? It is usually denoted by sequence Sn or sequence Sk. So if I'm taking it to be Sn, the way in which I define the term Sn is by taking the sum of first n terms alone. That is, I'm not taking the infinite sum. I am taking a finite sum with the condition that I'm taking only the first n terms of that sequence given. Just like we have plenty of sequences, I can always associate a series to any sequence that I have. So here I'm just focusing on few named series which are of great importance to us later. So which are geometric series defined by sum n equal to 0 to infinity r power n, where r is a real number. That is, here we are taking that r to be a fixed value and that n is ranging from 0, 1, 2, etc. Then second one is P series. So it is given by summation n equal to 1 to infinity 1 by n power p. So here p is a fixed value and this p is taken to be within the range closed interval 0 infinity. Then the third example is of harmonic series, which is in fact a special case of P series, which is sum n equal to 1 to infinity 1 by n. And the fourth example is telescoping series, which is sum n equal to 1 to infinity 1 by n into n plus 1. So just like we have discussed the convergence of sequence, we'll be discussing about convergence of series, right? So a series summation n equal to 1 to infinity xn is said to be convergent if the value of the sum exists. That is, when we are taking the summation value, it should be some kind of a finite value, right? That is when we say that the series is convergent. But the difference is, like when we have seen sequences, other than convergence, we had two cases, oscillating and divergent, right? In oscillating itself, we were having finite oscillation and infinitely oscillating. But in case of series, there is no such case. If it is convergent, okay, fine. Otherwise, the other case is only divergent. We are not having something called oscillating in case of series. So now we are just checking the convergence of some series. So I have taken the same examples which we have defined just now. So the first one is geometric series. We'll see why we have taken the convergence or divergence of these series when we are coming to the convergence test, right? So the first one is geometric series. So as we have told that R is taken from 0 to, sorry, here it is a correction, it is a real number. That is, I have taken R to be a real number. Sorry, it is from 0 to infinity itself. It was a correction here. I'll be making that correction while I'm sending it to sir. So here R is taken from 0 to infinity. So once I fix that R, it depends on that R whether the series is convergent or not. So if the R is from closed interval 0 to open 1, then the series is convergent, and otherwise it is a divergent series. And in particular, if it is convergent, then I can represent the sum. It is almost an approximation. We cannot say that that is the actual value. It is just an approximation, right? So it is around 1 by 1 minus R. Then second case is of P series. So in P series also, we have said that P is taken in, before itself we are considering that P. So P is taken as fixed. So here also it depends on the P whether the P series is convergent or not. So if P is greater than 1, then the series is convergent, and otherwise, that is, if P is in closed interval 0, 1, it is divergent. So just like we have told before, harmonic series, it was a special case of P series. So due to the same reason, so here we have said that for P in closed interval 0, 1, P series is divergent. So obviously here the P value is 1, so harmonic series is divergent. And next one is telescoping series. Telescoping series is also convergent. So the way in which we are finding out, so most of the time we are not computing the value to which the series converges. We are only checking whether it is convergent or not. But in questions that are given in exam, of course, there are questions that are asking for the series value, to the value to which the series converges. So we'll be handling such questions. So here, in case of telescoping series, we have been given the term, general term to be 1 by n into n plus 1. So we are splitting the term as 1 by n minus 1 by n plus 1. So what I'm doing is I'm taking the partial sum, right? I'm taking Sk, which is summation n equal to 1 to k, 1 by n into n plus 1. And what I'm doing is I'm applying the values from 1 to k. So what it becomes, for n equal to 1, it becomes 1 minus 1 by 2. Then I'm putting 2. It becomes 1 by 2 minus 1 by 3, and so on. So what happens is consecutive terms keep on cancelling, and what is left is 1 minus 1 by k plus 1, right? So what it becomes, this is for Sk. What I need is the infinite sum of this. That is, I need to tend my k to infinity. So the series sum becomes limit k tends to infinity, sum n equals to 1 to k, 1 by n into n plus 1. So I just have to take the limit of this value which I have obtained. So it becomes 1. So I can say that telescoping series is convergent, and along with that, the value to which it converges is 1. So again, like sequences, we are more concerned about the convergence of a series that is given. So here we are defining it using partial sums, right? So the first theorem is the case when the sequence which we have taken is simply a sequence of real numbers. No other conditions are applied, right? So let xn be a sequence of real numbers. Then we can say that the series produced using that sequence converges if and only if the sequence of partial sums is convergent, right? Only if this sequence converges to a finite value, then only I can say that the corresponding series is convergent, right? And coming to the second theorem, we are making some more adjustments to the sequence that we have taken. Like previously we said that xn was a sequence of real numbers. Now we are making it little more stronger by taking non-negative real numbers, right? So if xn is a sequence of non-negative real numbers, then I can say that the series converges if and only if the sequence of partial sums is bounded. That is, it is somewhat relaxed. Once I am making the condition on one side stronger, the condition on the other side is relaxed. So it is not required that the sequence of partial sum is convergent. It is enough that it is simply bounded. So those are two theorems relating to convergence. And two more. So the first one in this section, which is not relating to the previous two. This is some more generalized, which is called the Cauchy criterion for series. So when we see this, we can recall that we had a Cauchy criterion for sequences also. So what we said in Cauchy criterion for sequences is somewhat applicable for series also. But what is the difference? So we'll see the statement, that is the series n equals 1 to infinity xn converges if and only if for every epsilon greater than 0, I can find a natural number k, such that if I'm taking an m and n value greater than that particular k, the difference between sm and sn, that is the partial sum, mth partial sum and nth partial sum, the difference is less than epsilon. So this is almost like saying that the sequence of partial sum is Cauchy, right? So it is the same thing which we have said earlier. That is, the sequence is convergent if and only if the sequence of partial sum is convergent. That is, here I am trying to say that my sequence of partial sum is convergent in nature. That is, it is Cauchy. So it is same as saying that my series is itself convergent, right? And then we have a result. So this is useful when we are coming to convergence test. So the statement is, if series n equal to 1 to infinity xn converges, then limit n tends to infinity xn equals 0. So this is only a one-side implication. That is, if limit n tends to infinity xn equals 0, we can never say that, or it is not a general result to say that series converges. So the most simplest example that we can take is harmonic series. So harmonic series, we have already said that summation n equal to 1 to infinity 1 by n. It is divergent in nature. So as we can see, the limit value of the terms is 0, but it is divergent. That is the most simplest counter example we can give for this theorem, right? So this is only a one-side implication. Then we are coming to convergence test for positive term series. So positive term series means every term. So when we are defining the sequence also, it is not required that every term is positive. We can take it like our usual example itself, 1 minus 1, 1 minus 1. So if I'm taking like that, when I'm taking the series of that, not every term is positive. Some are positive and some are negative. But here we are talking of the case where all terms in the series, that is every element in that sequence, is strictly positive, right? So we are talking about the convergence test for such series. So I'll be mainly focusing on these tests, that is nth term test, comparison test, limit comparison test, Cauchy's root test, D'Alembert's ratio test, and Cauchy's integral test. There are other convergence tests, like there are tests which are used when root test or ratio test fail. But I found that most of the time when we are applying it for exams, most of the time, I'm not talking about special cases, I'm talking about the general case. So most of the time these tests are enough, and we have a few other results also which we can convert it to these forms and then solve using these basic tests itself, right? So we'll be focusing on these 6 tests only. So the first one is nth term test. So this is almost like the contrapositive statement of the theorem we have told just now, right? So we have said that if series xn converges, then the limit of the terms is 0. So I'm taking the contrapositive of the statement, that is, if limit n tends to infinity xn is non-zero, then series Xn does not converge. So that is my nth term test, right? So if limit n tends to infinity, Xn is non-zero, then series Xn diverges. So that is just what we have told earlier. That is, if it is not convergent, the only possibility is that of divergence. So the series is divergent. So this is only for checking divergence. We cannot check convergence using this test, right? Coming to the next test, it is called the comparison test. So just like the name states, if we have a series whose convergence or divergence is to be checked, we need to take one more series whose convergence or divergence is already known to us. Okay, and we'll be comparing that series with the series whose convergence or divergence is to be checked, right? So here I am having two positive term series. There also it is important that the series that I am taking for comparison should also be a positive term series, right? It should not be any kind of series. It should be a positive term series. So if series un and vn are two positive term series, and I can find a natural number m such that after that m, all the terms are comparable for un and vn. That is, un less than or equal to vn for all n greater than or equal to m. Right. That is, from the very first term onwards. It's not required that from the very first term onwards this inequality holds. At least we can find some value after which this inequality holds. Right. So in that case, I can say that the series un is convergent if and only if the series vn is convergent, and at the same time vn is divergent. Series vn is divergent if series un is divergent. So it depends on what we are doing. Like if we are given the question to check the convergence or divergence, if I can find a series whose terms are holding this condition, if it comes on the left side, that is, it is less than or equal to, which is convergent, then it is of no use. Because according to the theorem statement, the series which is convergent, its term should be bounded above. And at the same time, if I am talking about divergence, it is not required that I get the series on this side. That is on the right side. I need to get it on the left side. So that is very important. That is where you place this terms of the series. That is very important, right? So that is about comparison test. Now we have something very similar to comparison test, which is called the limit comparison test. So here also, it is almost like comparison test. So I need one more series, which is completely comprising of positive terms only. And here the condition is using limit. Here we were simply comparing it and then applying convergence or divergence. But here we are putting limit. So I called as limit comparison test. So I have two positive term series, series un and series vn, along with the condition that limit n tends to infinity, un by vn equals l, right? So here, what the conditions? We have three conditions. First one, if L equals 0 and series Vn is convergent, then series Un is convergent. Second condition, if L is infinity and series Vn is divergent, then series Un is divergent. And third condition, if 0 less than L less than infinity, that is, it is a finite limit, finite non-zero limit, then both series Un and series Vn behave alike. So I'll just explain it once more. That is, if L is 0 and we know that Vn is convergent. So here it is required that we should know about Vn, whether it is convergent or divergent. Similarly, violation of this condition also we cannot say about the conclusion. That is, I am getting L equal to 0 and I am taking series Vn to be a divergent sequence. Nothing is to be done. Okay, so we have to take the series in such a way that these two conditions are satisfied. So if L equals 0 and series Vn is convergent, then I can say that series Un, which is placed on the numerator, it is convergent. Then secondly, if L is infinity and the series Vn is divergent, then series Un is divergent. And when it is a non-zero finite limit, both series un and vn behaves alike. That means if vn is convergent, then series vn is convergent, then series un is also convergent. And if series vn is divergent, series un is also divergent. That is what it means, giving behaves alike, right? Then we have Cauchy's root test. So here everything is just like what is in its name. That is, if we are having a positive term series, here what we are taking is we are taking the nth root of nth term and finding its limit, right? So limit n tends to infinity, un power 1 by n. If I get that value to be L, then if L is less than 1, I can say that series un is convergent. And if L is greater than 1, then series un is divergent. And if the value is obtained to be 1, then the test is inconclusive. That means we cannot obtain a conclusion from that. The series may be convergent or divergent, right? So there are cases when we are taking like that, where we obtain the value to be 1, and at the same time one case is convergent and the other case is divergent. We have counter examples for that, right? So for this case, it is required that it should be a value other than 1 which is obtained for this limit. Coming to the next test, which is the ratio test. So here again we are having a series which is a positive term series. We are taking the ratio of consecutive terms, right? That is limit n tends to infinity, un plus 1 by un. If I get the value to be L, here also it is around 1. That is, the convergence and divergence is defined by the left side and right side of 1. So if L is less than 1, we can say that the series is convergent. And if L is greater than 1, we can say that the series is divergent. And just like root test, if L equals 1, then the test is inconclusive. So just like I've told in the very beginning, so we have tests like Rabi's test, logarithmic test and all, which are used when ratio test is inconclusive. That is when we are getting L equal to 1. But most of the time I didn't find any questions which are using these. They are using some other twisted ideas apart from using these direct test, right? So why I didn't include them in my lecture part.
Excuse me, ma'am.
Yes.
Ma'am, your voice is not clearly audible.
Is there an issue for everyone?
No, Nandana. Yeah, your voice is okay, Nandana. No problem.
So the person who said, I think it may be some kind of network issue in your side.
Yeah, it may be. You can continue.
Okay, sir. And the last test that we are going to discuss is Cauchy's integral test. So if I can convert my series, the terms in the series, to a non-negative monotonically decreasing integrable function. That is the case for Cauchy's integral test, right? So if u is a non-negative monotonically decreasing integrable function in such a way that u of n, that is when I'm taking the values for natural numbers alone, then I am obtaining it to be the terms of the series that I have taken, right? For all positive integral values of n, then the series un and integral 1 to infinity ux dx behaves alike. So, which means the series is convergent if this integral value is finite, and it is divergent in the other case, right? So actually, when we were talking about the convergence in these examples, right, this P series, harmonic series and all, actually the proof is given using this Cauchy's integral test, right? It is using this improper integral and all, that we are proving it is convergent for P greater than 1 and divergent for P between 0 and 1. Fine. So since we have not already discussed Cauchy's integral test, I could not include that in that part. So that is all about positive term series convergence. Next, we are coming to another type of series, which is called the alternating series. So when we were talking about positive term series, we are told that every term is strictly positive, right? We cannot have zero or negative terms in that series. So when we are talking about the alternating series, just like its name states, it is alternating between positive and negative. The sign of the terms are alternating between positive and negative. That is, it is of the form summation minus 1 power n xn or summation minus 1 power n plus 1 xn. Usually we use this first notation only, right? So that is what is called an alternating series. So again, we are concerned about the convergence of this series. So we are going to talk about convergence of alternating series. This is the most important test that we use for convergence of alternating series, called the Leibniz test. So here it has very strict conditions. That is, xn be a monotonically decreasing positive sequence that converges to 0. So we are talking about the sequence that we are taking first. So it is a monotonically decreasing positive sequence. That is, this is the condition, and that its limit value is 0. Then the alternating series sum minus 1 power n xn converges. So if these two conditions hold, I can say that my alternating series defined using this sequence converges, right? So this is the Leibniz test for convergence of alternating series. And then we are coming to one more test for alternating series. So in order to say that, we need to define two types of convergence, which is called absolute convergence and conditional convergence. So what is absolute convergence and conditional convergence? So a series xn, whichever be the series, I'm not talking in particularly about alternating series, any series xn, it is said to be absolutely convergent if sum of absolute values of those terms is convergent, right? So when we are talking about the case of positive term series, both these series are same, right? So it is only relevant when we have terms which are not positive, or when we are having negative terms along with it, right? And this is the theorem that we were looking for in case of alternating series, right? That is, every absolutely convergent series is convergent. That is, absolute convergence implies convergence. So, which means that if I am given an alternating series, and if I am able to show that it is absolutely convergent, then I can say that it is convergent. That is, what I'm going to do is, I'm going to take the sum of mod xn. That is, this is the definition. So I have to check the convergence of mod xn. So when I'm taking mod xn, it will definitely be a positive term series, right? Because the terms in alternating series are alternating between positive and negative. So when I'm taking the modulus, all the terms become positive. So which means I have obtained a positive term series. So I'll be checking the convergence of it using any of the tests that we have already discussed, right? And we'll be checking the convergence. And if it is convergent, then I can say that the alternating series that I have got is convergent. Now, what if it is not convergent? That is, summation mod xn is not convergent. That is where we usually apply the Leibniz test, right? So there, in that case, when absolute convergence test is failed, we'll be looking for Leibniz test. So there comes the definition of conditional convergence. That is, a series xn is said to be conditionally convergent if the series is convergent and series mod xn is divergent. That is, when we were checking for summation mod xn, it turned out to be divergent, right? But when we are checking it using Leibniz test, the series is found to be convergent. That is where we say that the series is conditionally convergent. And this is three results that we'll be using. So if we are having two series AN and BN, if both are convergent, then the sum of those two series is also convergent. If one is convergent and one is divergent, then the series, sum of their series is always divergent. And if both series are divergent, their sum can be convergent or divergent. So we have the counterexamples here. That is, if I'm taking an to be minus 1 power n and bn to be minus 1 power n plus 1. So if I'm taking the sum, it is 0. So it becomes sum 0, which is 0 itself, which is a convergent series. And if I'm taking an to be 1 by n and bn to be 1 by n plus 1, both are independently converging to, both are independently divergent. And at the same time, when we are taking the sum also, it will be almost like twice sum of 1 by n, which is again divergent. So these are the theory part that I am going to discuss and the tools that I'll be using. Any doubts? We are going to the problems. So if you have any doubts regarding the theory part, which is from the part that I've taken.
Excuse me, ma'am.
Yes.
कंडीशनल और एब्सोल्यूट वाला 1 मिनट दिखाएंगे क्या?
Yeah, this one.
हाँ, कंडीशनली के बारे में एक बार और बताइए, आपने जिस तरीके से बताया.
Can you speak in English? I am not so good.
Can you explain once more?
Yeah. So we have said that if series mod xn is convergent, then obviously the series is convergent using this theorem, right? But what if this mode, sum of this mode value is not convergent? Because this is only a one-side implication, that is absolute convergence implies convergence. But what if it is not absolutely convergent, right? So when this condition fails, we'll be applying the Leibniz test, right? That is directly for alternating series. We are not taking the modulus value. So in case it is convergent, so I'll give you an example for conditionally convergent sequence. We are taking summation minus 1 power n by n. Plus of that term, it is 1 by n, right? So if I'm taking the sum, it is sum 1 by n, which is my harmonic series, which is divergent. But if we are checking the series as such, we'll go to Leibniz test. So it is a decreasing sequence, right? 1 by n is decreasing, and at the same time, its limit value is 0, which means that my series of minus 1 power n by n is convergent, right? That is, my modulus series is not converging, but the actual series is converging. That is what is called as conditional convergence. Is that okay?
Okay, thank you.
Okay. Any other doubts or any parts which you need any repetition or clarification? If not, we'll go to the problem session. Okay, I think I can move on to the problem part. So this is the first question. That is, the sequence Sn of real numbers given by Sn equals, it is given as sum of n terms, right? So the terms are sine pi by 2 by 1 into 2 plus sine pi by 2 square by 2 into 3 plus etc. plus sine pi by 2 power n by n into n plus 1. So it is asked about the convergence, divergence, or oscillation of this sequence. So you can check the question and you can start giving answers which you feel like it looks like the answer of this question. So any answers? It looks like a question in sequences, but is actually something in series. I hope I am audible. I think I am getting answers in the chat box, right? Option 4. Okay. 2 of you has said it is Cauchy in nature, that is, it is convergent. Any other answers? Cauchy sequence.
It converges at 0.
Sorry, I can't hear you properly.
It converges at 0.
Okay, we are not bothered about to which value it converges. We just need whether it is convergent or not. So you're saying that it is convergent, right?
Convergent, then it is Cauchy.
Okay. Any other answers? Is there a voice issue in my class?
No,
No, ma'am.
no problem.
Okay. I can find some messages stating that there is some kind of voice issue. So why I asked. Okay. So do we have any other answers? We have got few answers, all of which are pointing to option 4. So let's see the answer. So here it is actually like taking the partial sum of a series, right? So we have been given that Sn equals n terms are taken, right? So if I am asked about the convergence of the sequence, so what is to be done? I have to find the limit of this sequence, right? So if I'm finding the limit of the sequence, it is almost the same as checking whether the series of comprising of terms of infinite type of this kind, whether it is convergent or not, right? That is, we are given that Sn equals series k equals 1 to n sine pi by 2 power k into n plus 1. That is how it is defined. So now we are taking the limit of this term, that is Sn. It becomes series k equals 1 to infinity sine pi by 2 power k by k into k plus 1. So this value if and only if the right side is a finite value, right? So here we are checking the convergence of the series on this right side, right? So here, as we can see, sine pi by 2 power k by k into k plus 1, it is always less than or equal to 1 by k into k plus 1. So can somebody say why I have applied comparison test here? That is, we are showing the convergence of this series using comparison of the term. That is normal comparison test. So why are we using comparison test here?
Then
Ma'am,
because
to
of sine pi upon 2 to power k is highest value is 1.
Okay, so when we are talking about range of sign, it is from -1 to 1.
Minus 1 to 1. If
So
for
here,
maximum value, then
so it is required that when we are applying the comparison test, it should be a positive term series. So here, when we are checking, we can see that we are taking the values, that is sine x. Here, x is ranging from pi by, or the values that x is taking is of the form pi by 2 power k, right? So it is from pi by 2 to almost like 0, So the values are, it is not reaching 0 anyhow, but the values are like pi by 2, pi by 4, etc. So all these values, that is sign of all these values, will be lying above x-axis itself, right, from the graph of sine. That is the reason why we have taken, that is, this is always a positive term sequence. That is sine pi by 2 power k by k into k plus 1 is always positive, right? That is the reason why we have taken comparison test. Okay. So as we have obtained the answers, it is Cauchy or convergent, and this answer is option 4. So we are moving to the next question. So we have a series which is defined by 1 by n power m into 1 plus 1 by n power p, where m and p are real numbers. So under which condition does the above series converge? So we have been given options for values of m and p, some range of values of m and p. So you can start guessing the answers.
Option 1.
Option 1. Okay. Any other answers?
Yes, ma'am, option 1.
Option 1. Okay. So anyone wants to argue with the people who have said option 1?
Ma'am, take un
Yes.
1 upon n. This is take un 1 upon n to power m plus 1 upon n to power p, and vn as 1 upon n to power m. Un
Okay.
upon vm is finite.
Yes, that is it. That is, we are applying limit comparison test, right?
And both.
Yes, so we are going to the answer, that is the explanation. So I've taken it as cases. So the first option was for m greater than 1, right? For m greater than 1 and for any p that I'm going to take, right? Whether m is positive or negative, n power p is positive because n is positive, right? 1 by n power p is also positive, and 1 plus 1 by n power p is also positive. Along with that, it is greater than or equal to 1. So I can say this inequality, that is 1 by n power m into 1 plus 1 by n power p is less than or equal to 1 by n power m for any p that I take, right? So by comparison test, I can say that the series is convergent. So option 1 holds. Now we are checking for rest of the options, that is for the cases of 0 less than m less than 1, 0 less than or equal to, 0 less than m less than or equal to 1, and m equal to 1. Similarly for p also. So here we are checking for p greater than 0 because, yeah, we are asked about p greater than 1, but we are talking of a more general case where we are taking p greater than 0. So taking limit n tends to infinity, what I get is, that is, I am comparing it with 1 by n power m. So here my m is between 0 and 1. So if I am taking 1 by n power m, this is a divergent series using the idea that for p series, if p is between 0 and 1, then excuse me, if it is between 0 and 1, it is divergent. So using that idea, I am comparing it with this term. So I am taking the ratio of this value. I get it to be 1 by 1 plus 1 by n power p. And for p greater than 0, this value, that is n power p, it becomes infinity. So I get that 1 by n power p becomes 0 and the overall value becomes 1. So from which I get that by limit comparison test, both these series, the series on the numerator and the series which is having term on denominator, they behave alike, right? So for m less than 1, that is between 0 and 1, I get that the series is divergent. Now we are looking at the case, third case. So here we are having P equal to 0 also. So we have already told for P greater than 0 generally in the second option. So we'll be talking particularly of the case where P equals to 0. So when P equals 0, it becomes 1 plus 1, right? Inside the bracket, it becomes 1 plus 1, which is 1 by 2 into n power m, which is again a P series. And what is the condition for m? It is from 0 to closed interval 1. So for all these values, we know that P series is divergent. So we get that in third case also, it is divergent in nature. And fourth one is for m equals to 1 and P greater than 1. That is combining this part and this part from option 2 and 3. So combining both, we get that it is again divergent in nature. So we get answer is option 1. That is for m greater than 1. Is that clear?
Yeah, ma'am.
Okay.
Yes, ma'am.
So we'll go to the next question. So this is regarding convergence, absolute convergence, etc. So we are given 4 series. 3 of them are demanding for convergence and 1 is demanding for absolute convergence. So you can start saying the answers once you are confirmed with it. You can use convergence test or any other ideas that we have discussed. So you can start guessing your answers.
B, ma'am.
B or D? 2 or 4? 2, okay. Okay, any other answers? Okay, one more answer has come, option 2. One of you has said option 1.
Madam, by Leibniz test, first one is
Yes.
convergent, I think.
Okay, so only option 1. It can be 1 answer, 2 answer, 3 answer, or 4 answer. It's not required that it is a multiple choice question. It can be a multiple answer question. So there is nothing wrong if you are getting more than 1 answer. So far we have got answers 1 and 2. No one wants to go for 3 and 4. Okay, one of you has given 1 and 4.
2 and 4.
Okay, now 3 is only left to come. Anyone has got answer 3? So I guess we can go to the answers. We have got some suggestions like 1, 2, and 4. No one has said 3. Right. So we'll go to the answer. First one, as the one who has already answered, he has said using Leibniz test. That's correct. So first option, we are applying the Leibniz test. So here, first, if we are checking, we are given an alternating series, right? So when we are checking using absolute convergence, this is more like 1 by root n or 1 by n power 1 by 2. So it is not convergent using the idea of P series. So which means I cannot apply the absolute convergence test here. So I have the only option that I have is Leibniz test. So using the Leibniz test, I can see that the sequence 1 by root n, it is decreasing along with the condition that its limit value is 0. So which means that the series is convergent in nature, that is using Leibniz test. Now coming to the second option, that is minus 1 power n by root n plus n. So here they have specifically mentioned absolute convergence. So I need not check this minus 1 power n. I need to check 1 by root n plus n, right? So here for second option, I have applied limit comparison test. I have compared it with 1 by n, right? So taking 1 by n, I get it as n by root n plus n. Dividing entirely by n, I get it as 1 by root n plus 1. Giving limit, it is 1. So using limit comparison test, I have got a finite value. So both 1 by n, series 1 by n and series 1 by root n plus n, they behave alike, which means since the harmonic series is divergent, the series that I have is not absolutely convergent. Actually here it is not divergent, it is not absolutely convergent, right? And coming to the third option, that is series 1 plus minus 1 power n into root n plus log n by n power 3 by 2. It looks really large, but when we are breaking it down into smaller series, what we get is, that is, I have taken the term of that series, I have broken it down into, I have opened this bracket, root n plus minus 1 power n root n plus log n divided by n power 3 by 2. N power 3 by 2 is n root 2. N root n, right? So here, when we are breaking down the term separately, so what we get is 1 by n plus minus 1 power n by n plus log n by n root n, which is n power 3 by 2 itself. Now we are taking each of these series, right? So series 1 by n, it is already divergent. We have discussed about it. Then series minus 1 power n by n, it is convergent using Leibniz test that I have given already as an example for conditional convergence, right? So this series is convergent. So now we have already told that sum of a convergent and a divergent series is divergent in nature, which means the sum of these two terms, the series comprising of these two terms, is divergent in nature, right? Next, what I am doing is I am applying the comparison test. I have one more term, right, which is log n by n power 3 by 2. So which is for natural numbers. So this value is definitely positive. So which means I am getting this value to be a positive series. So here when I'm applying it, we get that, yes, that is when we are comparing it, we get that the series is divergent in nature, right? And the final option, which is summation minus 1 power n root n plus 1 by n power 3 by 2. So when we are coming to it, we get that, again, we are breaking down the sequence term. So minus 1 power n root n plus 1 by n root n, right? So when we are breaking it down and applying it as two different series, we get it as minus 1 power n by n and 1 by n power 3 by 2. So this series is convergent by Leibniz test, and this is P series with P value greater than 1. So both these series are convergent, and hence we get that both series converges, right? Is that okay?
Ma'am, 1 upon root n is convergent or divergent? Because of the P is
Which
less
one?
than 1
This one.
in first option. 1 upon
Your
root n.
voice is breaking. I can't hear you properly.
Ma'am, 1 up in first option, 1 upon root
Yes, this one.
n. T is less
Yes.
1.
Mm.
1 upon n to power p, where t is less than 1. Then conversion to divergent.
It is convergent. You're talking about option 1, right?
But t series test for less than 1 is divergent.
Yes, that's what I was talking about. That is when we are taking absolute convergence. Of course, it is not convergent because it is a p series with p value less than 1. So absolute
Con-
convergence is only a one-side implication for convergence. That is,
It
it
is
is
conditionally
absolutely
convergent.
convergent. Yeah, it is absolutely convergent implies convergence. But what if it fails? It is not,
This
nothing is
is
told when the case. Yeah,
this is conditionally convergent.
I can't get you.
This is conditionally convergent.
Yes, yes, it is conditionally convergent. That is, the series itself is convergent. So that is actually just two type of definition. It is convergent. Is the definition confusing you? Is it okay now?
Okay, ma'am.
Okay.
I find conditionally convergent, then I
Yeah, actually conditionally convergence is convergence itself. But the only problem is that it does not hold the condition of absolute convergence. Okay. That is when I say that the series is convergent, it's the sum of, that is the series of its modulus terms may or may not converge, right? So in the case where that series of modulus term does not converge, that convergence I call it as conditional convergence. That's all. There is nothing to get confused in that. It's just the formal definition of that. I think this is clear and I can move to the next question, right? So this is the next question. That is, we are having a sequence of positive real numbers. The series an converges if we have been given 4 different series. So the question is, upon convergence of which of these series, I can say that series an is convergent. That is the question. So you can use theoretical ideas or counter examples, whatever.
option 4.
Option 4. Okay. Any other answers?
Ma'am, option 3.
Option 3. Okay. Any other answers? One person has commented as option 3.
Ma'am, option 3.
Okay, option 3. Option 1 and option 4 has come. Option 3.
Option 1.
Option 1. Okay, then. I guess we can slowly move to the answer, right? So here, the question needs to be clear. That is, which of the convergence implies convergence of AN? That is the question. So when we read it for the first time, it is easy to get confused that the series convergence implies which of the following? That is the wrong way, right? So we need
First and fourth, ma'am.
So here we take the answer is option 3 itself. So first one, we are taking counterexample as series 1 by n square. So using the idea of P series, this is convergent. But at the same time, series 1 by n, it is not convergent, right? So that is first counterexample for option 1. So option 1 is wrong. Now taking second option, I am taking an to be 1, right? So it becomes series 1 by 2 power n. So that is a geometric series with r value less than 1. So it is convergent in nature, and thus I get that it is convergent. So considering series an, right, that is what we need to check. It is series 1, which is definitely not convergent in nature, right? So option 2 is also false. Now coming to option 3 and 4, it is using the idea of ratio test, right? So just like I've told, you can use ideas, the theoretical ideas or counterexample, whichever is comfortable for you, right? Okay. So I'm taking series an plus 1 by an, right? First option. So it is given that it is convergent. So we have already used the result that if the series is convergent, the limit of the nth term or the limit of the nth sequence value is convergent to 0. So here what I get is limit n tends to infinity, an plus 1 by an is 0. So by ratio test, what do we have? The limit value is less than 1, which implies that the series is convergent. And similarly, taking it the other way, what we get? Limit n tends to infinity, an by an plus 1 becomes 0 when this series is convergent. So what do we get? The limit of its reciprocal becomes infinity. It is tending to infinity, whose value is definitely greater than 1, which results in the conclusion that series an is divergent in nature. So we get answer to be option 3. Right? Is that clear?
Yes, ma'am.
Ma'am.
Okay. So this is the next question. That is A and B a real sequence converging to A, where A is greater than 0. Then what can you say about series an and series an by n? Whether are they convergent or are they divergent? We have to talk about both the series.
Option 1.
Option 1, that is an converges and series an by n diverges. Okay. Any other answers? Is it because the questions are too tough, or is it because you are not trying to calculate it there? I have got only one answer till this time. Are there any answers in the chat box? Okay, option 1 and 3 is coming. So most options are saying that series an is convergent. Confusion is only regarding series an by n. Okay,
Ma'am, I
so
think both are convergent.
both are convergent. That is option 3. Okay, so 1 and 3 is coming simultaneously. Sorry to disappoint you, but the answer is option 4. Because we are talking about series AN, not sequence AN. So AN converges to a value does not imply that series AN is convergent. So here we are applying the nth term divergence test, right? We were told that limit n tends to infinity, xn is non-zero, implies series xn is divergent. So here it is given very clearly that an is a real sequence which is converging to a, and a is greater than 0. There itself the statement is very clear. So which means that series an is divergent in nature. So option 1 and 3 are cancelled out there. Now we need to check about series an by n only. So what we are doing is either we can go in theoretical side or we can take counter example. Right. So I have taken counter example here. So I have taken an to be 1 plus 1 by n. Okay. So it is a real sequence which is converging to a positive value. Right. It is converging to 1. So when I'm taking an by n, it becomes 1 by n plus 1 by n square. So taking the series, I get it is series 1 by n plus series 1 by n square. One is divergent and the other is convergent. So what do we get? It is a divergent sequence. Sorry, divergent series. Or when we are taking it to the theoretical side, what we get is we are taking the limit value, limit of this term. So it becomes limit of the numerator is a and limit of denominator is going to infinity. But sorry, we have to take it like in the case of limit comparison test. That is 1 by n. Taking 1 by n, we get that an by n by 1 by n. So we get it as limit an value is positive. So which is a finite value, which means that an by n and 1 by n behaves alike. And as series 1 by n is divergent in nature, we get that this series is also divergent. Right. So don't confuse convergence of sequence with convergence of series. Both are two different things. Right. So is this explanation clear? This was actually a simpler question because nth term divergence statement was clearly given in the question. So is the explanation clear?
Yes, ma'am.
Okay. Is there any doubt?
Clear, Anna?
Okay. In counter example, an can be 1. An can be 1. But one sec, let me check. An be a real sequence. Yeah, of course, we can take a simple counter example as an equal to 1. That is the right way also. Very good. So we'll go to the next question. So an is a sequence of real numbers. Which of the following is true? So here also the convergence is circulating about the series an and to some other power of the terms, and two options are regarding series modulus an and power of the terms. So you can start saying the answers if you have found any. Option 2, one of you has commented it as option 2, option 4, okay, 1 and 2,
1 and
Okay, 1 and 2. 1.
this is single choice.
Sorry.
This is a single choice.
I can't understand you clearly.
In this question, only one option is true.
Which of the following is true?
Ma'am, it is MCQ or MSQ?
Actually, you shouldn't be asking that question. What if the question is in the section of MSQ? So if it is an MSQ, you cannot be sure whether it is 1 answer, 2 answer, 3 answer or not. So you have to find out the answers. So many people are settling to option 2. So should I go to the answer now or you need more time? Option 1 seems to confuse everyone, it seems. Option 3. Okay. Okay, I think we'll slowly move to the answer, right? So the answer is option 2. 1 is not true. So I've taken a counterexample. I've taken an to be minus 1 power n power 1 by 4, right? It is given as a sequence of real numbers. It's not told that it is positive sequence. It is any sequence, right? So I've taken it as an equal to minus 1 power n by n power 1 by 4. So when I'm taking the fourth power of it, what will I get? So this series is convergent, right? Series an is convergent using Leibniz test. But what about an power 4? Here minus 1 becomes 1 and denominator becomes n, which means it is the harmonic series, which obtains the answer that series an power 4 is not convergent, it is divergent. Now the second case, we are taking series an converges, then series an square converges. So here, whatever be the series that I am taking, whatever be the terms that I am taking, so if we are considering it to be, actually the question was little more strong. There was a mistake in what I have written. It was sequence of non-zero real numbers, right? I missed that point here. So here, when I'm taking that, I'll be correcting that and sending it to you, okay? So here, if I'm taking that as, that is according to the question, when it is a non-zero sequence, I get that series mod an is convergent. So mod an, it is definitely positive. So series mod an is a positive term series. So this is convergent. And an square. So it is an even power. So definitely the terms an square is also positive in nature. So both the series that I have are positive term series. So I am going to apply my limit comparison test to them. So I get, along with that, I have the condition that limit n tends to infinity mod an is 0. This is because my series mod an converges. So I get limit n tends to infinity an square by mod an. It becomes limit n tends to infinity an, which is 0, right? So by limit comparison test, I get that my series an square is convergent in nature. So that option turns out to be true. Now for 3 and 4, again I have taken counterexample. That is, for third one, I have taken an to be 1 by n. So series 1 by n is divergent, but series 1 by n power 3 is convergent. due to the reason of P series with P greater than 1. And again, coming to 4, I can take it as some kind of alternating series or simply as 1 by n itself. I have taken as minus 1 power n by n. So series mod an, that is a series 1 by n. It is divergent in nature, but series 1 by n square, that is an square, it is convergent in nature, which contradicts our option 4. So I get my answer as an option 2. So is that explanation
Ma'am,
clear?
hello.
Yeah, tell me. Actually, there was a correction in the
Ma'am,
question. I'll make
option
that when I'm sending it. Okay, tell me.
for counter example 1 purpose, we can take 1 by n to the power 1 by 4. No need to minus 1 to the power n. Is it possible?
Are you asking whether this is convergent or not?
No. For counter example purpose, I can take 1 by n to the power 1 by n, 1 by 4. This is
Okay.
convergent. This is
No,
convergent. Then
But when we are taking 1 by n power 1 by 4, it is a P series with P value less than 1. It is not convergent. So there, the assumption that we are taking itself is wrong. So we cannot say that series an is convergent. So I have just adjusted that as minus 1 power n by n power 1 by 4. Okay.
ma'am, then second option purpose we can take minus 1 to the power n by n to the power root n.
Minus 1 to the power
N. Then mod absolute series is not convergent. Okay, I understood.
Okay. Is it clear now?
Yes.
Okay. So I hope there are no more confusions. We can go to the next question. So the next few questions that I am going to discuss is regarding finding the sum of the series. Right. It is not asking whether the series is convergent or not, because it is crystal clear that when we are asking to find the sum of the series is convergent. Right. If it is divergent, they will not ask to find the sum. So we have to find the sum of the series. So when we come to such questions, we need to apply some kind of computations in that. Maybe we'll require some kind of identities. Okay. So we should be ready with some expansions, identities and all. Right. So this is the first question. We are asked to find the sum of the series 1 by 2 into 2 square minus 1 plus 1 by 3 into 3 square minus 1 plus 1 by 4 into 4 square minus 1 plus etc. So this was a numerically answering type. So we don't have any options. You will have to compute it by yourself. At least you can just tell me the idea what can be used rather than computing the entire thing. So one of you has given the answer as 1 by 4. Okay. If you are finding it time consuming to compute the entire thing, just share the idea. What can be used to find the sum in this case?
Partial fraction.
Partial fraction. Okay. Any other idea that anyone wants to give? So I have obtained one answer as 1 by 4. Someone has commented it as Leibniz. It's actually not, we are not actually testing the convergence. We are trying to find out the sum of the series. So we are not looking for convergence test. Now, next few questions, just forget the convergence test. We are going to compute some series. So we need ideas what can be done.
सेम वही करना पड़ेगा मैडम.
Sorry? Yes, partial fraction. Okay. We have got two answers as partial fraction. Okay, we'll see the answer. Right, so the answer is correct. We have to apply partial fraction to it. So in what way we are going to apply, we'll see that. Okay, so the series, it is given as 1 by 2 into 2 square minus 1 plus 1 by 3 into 3 square minus 1 plus etc. So I am writing it into the series form, that is series k equal to 2 to infinity 1 by k into k square minus 1. So I am splitting, I am keeping the 1 by k aside and I am computing only for this 1 by k square minus 1, right? So it becomes 1 by 2 into 1 by k minus 1 minus 1 by k plus 1. So when you're taking the LCM, you can see that evidently, right? Denominator becomes k square minus 1, numerator becomes k plus 1 minus k plus 1, which is 2. So striking off both the 2 from numerator and denominator, we get this value itself. So this is how we are splitting it. So now we are trying to find out the series sum. So that is same as taking the limit of partial sum, right? That is, I am taking this 1 by 2, it is remaining as constant. So I have taken 1 by 2 outside, taking limit n tends to infinity, series k equal to 2 to n. I have restricted it till n. 1 by k into k minus 1 minus 1 by k into k plus 1, right? So 1 by 2, I am keeping the limit there itself. I am applying the values 1 by 1, right? So putting 2, I get it as 1 by 2 into 2 minus 1, which is 1, minus 1 by 2 into 2 plus 1, which is 3. So these two terms are for putting k value equal to 2. Now putting k equal to 3, I get 1 by 3 into 2 minus 1 by 3 into 4. So it goes on like this. So here itself we can see a pattern that consecutive terms are of opposite sign. So they cancel each other and the final terms that are left are 1 by 2 into 1 and the last one, that is 1 by n into n plus 1. So I have to apply limit for this value. After all the computation, this is what I have. So applying limit, I get 1 by 2 minus 0, which is 1 by 2 itself, and the final value is 1 by 4. Right? Is this explanation clear?
Yes, ma'am.
Okay. So when it comes to computing of series, that is, rather than checking the convergence of a series, when we are finding the sum of series, it is slightly different. Most of the time, we cannot apply same idea for all questions. Each question is different, right? Once we are solving the examples that I've taken, you will understand that, because I've taken, I guess, 5 questions to find out the sum of the series. All 5 are different, right? Here we have applied partial fraction for just one part. That is, I've kept my 1 by k aside and I have applied partial fraction to rest of the term. Now we'll see next question. Right.
Ma'am,
Yes.
that was is that a telescoping series?
Telescoping series, yes. Individually, these are telescoping series. That is 1 by k into k plus 1. It is telescoping in nature. Yes. But here we cannot apply that idea directly.
Okay, madam.
Okay. So we are going to the next question. This is, here we have options. Thankfully, we are having 4 options for guessing. So the sum of the series is given as 1 by 2 into 3 plus 1 by 2 power 2 into 3 plus 1 by 2 power 2 into 3 power 2 plus 1 by 2 power 3 into 3 power 2 plus etc. The general term is 1 by 2 power alpha 3 power alpha plus 1 by 2 power alpha plus 1 3 power alpha. So we are asked to find out the sum.
3 by 10.
3 by 10. Okay. 3 by 10. Two answers have come. Any other answers? If this is all we have, okay, option 2. So I think most of it, that was somewhat easier it seems. Okay, we'll see the answer. Answer is correct. So the way in which we are proceeding is, I've taken the general term just like they are given. So we are taking summation k equals 1 to infinity 1 by 2 power k 3 power k plus 1 by 2 power k plus 1 3 power k. So what I'm doing is I'm taking 2 power k 3 power k commonly outside. So what remains is 1 plus 1 by 2, right? So this 2 power k 3 power k is 1 by 6 power k. And this 1 plus 1 by 2 becomes 3 by 2. So 3 by 2 being a constant, I have taken it outside. And what remains is summation k equal to 1 to infinity 1 by 6 power k. So this is clearly a geometric series with value less than 1. So in that case, we have obtained that series sum is approximately equal to 1 by 1 minus r, where r is the term that is keeping on increasing. Right. So here my r value is 1 by 6. It becomes 1 by 6 by 1 minus 1 by 6. That is 1 by 6 by 5 by 6. So 3 by 2 into 1 by 5, which is 3 by 10. So this was comparatively a direct kind of calculation. So is there any doubt?
No, ma'am.
Okay.
No, ma'am.
Fine. So we'll go to the next sum. Sum of the infinite series s equals 1 by 2 minus 1 by 3 into 1 factorial plus 1 by 4 into 2 factorial plus 1 by 5 into 3 factorial plus etc. That is, sign is keeping on changing. In denominator, we can see that values are increasing from one side. On the other side, factorial is increasing. And we are asked to find out the sum of the series. So from the option itself, it is clear that we need the expansion of e power minus 1. So it is required that the expansion of e or the exponent function is required. Is someone saying an answer? Okay, can someone tell me the expansion of e power x?
1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus etc. ma'am.
Yes, that's it. So in that expansion, we have to put x as minus 1. So is there some way you can connect this sum to that value? That is what the options demand. So any answers? Anyone is able to connect to some value? Is there an answer?
Second option.
Second option. Okay. Any other answers? If not, we'll go to the answer, right? So I've taken my answer is correct, option 2 itself. So we'll see how the series is reaching to that sum value. So S, as the question has given, it is 1 by 2 minus 1 by 3 into 1 factorial. So when we are observing the term, we can see that it is almost like n plus 1 into n minus 1 factorial. So there is an n missing there. So what I'm going to do is, for each of the term, I am going to multiply that particular n in numerator and denominator. So here it is same itself, 1 by 2 factorial. From the next term onwards, it becomes 2 by 3 factorial plus 3 by 4 factorial minus 4 by 5 factorial plus etc. Right. So I have reshaped my series as series n equal to 1 to infinity minus 1 power n plus 1 into n by n plus 1 factorial. Right. So I am going to keep this minus 1 power n plus 1 aside. I am going to take this n by n plus 1 factorial. So writing it as n plus 1, taking the numerator as n plus 1 minus 1 and splitting it, I get it as n plus 1 by n plus 1 factorial minus 1 by n plus 1 factorial, which becomes 1 by n factorial minus 1 by n plus 1 factorial. Right. So here, again, when we are seeing this example, it looks like we can apply that 0, 1 when we are taking the limit as partial sum, but we cannot apply that idea here. That is what I'm talking about. That is, each case when we are finding out the sum, they have different approaches. Okay, so here we cannot take it as partial sum and keep cancelling the terms. So how we are proceeding is, that is a sum of the series. I am taking it, that is, I'm resubstituting it to what I have stopped. From where I have taken the term, there itself I am replacing this value. That is minus 1 power n plus 1 into 1 by n factorial minus 1 by n plus 1 factorial. So keeping 1 minus 1 there and taking rest, that is minus 1 power n to both the terms, I get minus 1 power n by n factorial. And here I am already having one negative. So it becomes minus 1 power n plus 1. Right. So this being a constant, I have taken it out of the summation and it becomes series n equal to 1 to infinity minus 1 power n by n factorial plus summation n equals 1 to infinity minus 1 power n plus 1 by n plus 1 factorial. So here if I am looking, I can see that from 1 onwards it is holding. Right. When it is e power x, its expansion is series n equals 0 to infinity x power n by n factorial. But here it is from 1 onwards. Right. That is, my value is ranging from minus 1 power 1 factorial minus, plus 1 by 2 factorial minus 1 by 3 factorial, etc. So I am missing a 1 there. So I am taking it as e power minus 1 plus here I am missing 2 terms, but they are both 1. That is 1 minus 1. Then rest I am finding it from 2 onwards. So why I have not included that term here. It is taken directly as e power minus 1. So upon further calculation, we get that it is minus 1 into 2 power minus 1 minus 1. So together 1 minus 2 power e minus 1 or 1 minus 2 by e. So is it clear? Is it convincing?
Yes, ma'am.
Yes, ma'am.
Okay. So we'll go to the next sum. This is the next sum. This looks little more crooked because till now we were talking about terms which can easily be taken as sum. But here we are having product also. So we need little more extensive calculation. And the hardest part is we don't have any options. You need to compute it yourself. So if required, I can help you by showing the answer, but you need to tell me what can be done. This is the answer. 1 by 2 into 4 by 3 power 2 by 3 minus 7 by 6. Any idea or any expansion that you can give for solving this question?
Ma'am, numerator and denominator arithmetic sequence.
Arithmetic sequence, okay.
And 1 by 4 square, 1 by 4 cube.
Okay, so how can you club that to find out the sum of the series? Of course, this question was little more complicated when I was doing rest of the questions. I think we'll go to the answer directly because this is little more lengthy, right? So this is the series that is given. The first step, LHS, right? So what I'm doing is I am multiplying entire numerators by 2 and I am dividing by 2, right? So I've kept this 1 by 2 outside, 2 into 5, etc. So you can see that 2 has been included in every numerator term, right? And in the second step, what I am doing is I am taking 3 as common factor from each denominator, right? So in the first term, I have 3 square into 1 into 2. In the second term, I have 3 cube into 1 into 2 into 3. Third term, 3 power 4 into 1 into 2 into 3 into 4, etc. Right. So we are trying to transform it into something that we can apply some identity or something like that. Okay. So now, in the next step, what I'm doing is I'm going to give these 3 as denominators to terms which are in the numerator. Right. That is 2 by 3, 5 by 3. So denominator, it remains as 2 factorial. That 1 by 4 power, whatever is the power of 4, I'm not changing that term. It is kept there itself. Okay. Only the coefficient of this 1 by 4 power k is transformed. Right. So here that 3 cube, I am giving it as 2 by 3, 5 by 3, 8 by 3. Here it becomes 2 by 3, 5 by 3, 8 by 3, 11 by 3. Right. Now what I'm doing is I am giving negative, that is minus value correspondingly without changing the sign of these terms. Right. So here I have only 2 terms. I am giving negative to both the terms. Here I have 3 terms. So upon giving negative to these 3 terms, it turns out to be negative. So I am giving one minus here also. Right. So this is how it proceeds. For for even values, we are simply giving the negative to each of these numerator fractions. And for odd terms, along with giving negative to these terms, we are also giving one more negative outside. Right. So this is how we have transformed it. Now, when we are looking at it, what will it look like? So I am giving 2 more terms to it and subtracting it together. Right, that is 1 by 2 into, these are the 2 terms that I have added and subtracted. That is 1 minus 2 by 3 by 1 factorial into 1 by 4. Right, I have added it here and I have subtracted it here. Right, inside the overall bracket. Now we are applying the formula or the binomial expansion of 1 minus x power n, which is given by 1 minus nx plus n into n minus 1 by 2 factorial into x square plus minus n into n minus, sorry, this was n minus 2, n minus 2 by 3 factorial into x power 3 plus etc. So now just forget these 2 terms. Look at this part, which is inside this first round bracket. So we can see that 1, so this is n and x. This is n into n minus 1 by 2 factorial into x square minus n into n minus 1 into n minus 2 by 3 factorial by x power 3, and so on. That is how it is proceeding. So I can rewrite this first round bracket terms as, that is, it turns out that my x value is 1 by 4 and n value is minus 2 by 3. Right, here it is 1 by 4 and here it is 2 by 3. Okay. So it becomes 1 by 2 into 1 minus 1 by 4 into minus 2 by 3, and rest of this, the term which we have subtracted, it is remaining unchanged. So it is 1 plus 2 by 3 into 1 by 4. So finally, just the numerical calculation. So it becomes 1 by 2 into 3 by 4 power minus 2 by 3 minus 1 plus 1 by 6, which is 1 by 2 into. So this is negative power. Making it as positive power, it gets inverted. The fraction gets inverted. So 4 by 3 power 2 by 3 minus this term, which is 7 by 6. So computing a series even without giving an option, it is hard, I know, but is this explanation clear? It is quite lengthy and time consuming, I know. So
Yes,
is
ma'am.
there any clarifications required?
Ma'am, 1 minus x whole to the power n equal to n into n minus 1 into n minus 2.
Yeah, it is n minus 2. That was a typos error. I'll clear that while sending the PPT. Okay. Is the explanation part clear apart from that typos error?
Yes, ma'am.
Ma'am.
Yes. Is any clarification required? Should I repeat any step? We are doing too many things on the series that we are given. But that is what we have to do to find the sum. No other way. So anywhere, any point where I should repeat? If it's clear, we'll go to the last question.
Yes, ma'am.
Okay. So this is the last question. So here it is another type, different from all the 4 types we have done. So here, rather than asking for a numerical value, they have asked for tan inverse of 2 by n square, sum of those terms. To which value does it sum up? So this is the last question. After solving this, we are done. So I can give you a hint. Since we are given that this tan inverse, it is giving us, the question itself is giving us a hint that we have to use some identity connecting tan inverse. Because we cannot find out the value for each n and keep on adding. So we need to apply some identity here involving tan inverse. So once you get that identity, rest is easy. Which identity of tan inverse is to be applied? Whether it's its expansion or some other identity involving tan inverse, something like that. So we are getting 3 and 1 as answer. So any one of you who got 3 as answer want to share the idea that you have used? Or the identity that you are going to use for this? If even this seems hard, we'll go to the answer. So this is the identity that we are going to use. Okay. Tan inverse x minus tan inverse y equals tan inverse x minus y by 1 plus xy. So what I'm going to do is, I am going to put x equals k plus 1 and y equals k minus 1. So what it becomes? Tan inverse k plus 1 minus tan inverse k minus 1 equals tan inverse. So just substituting it here, I get it as tan inverse 2 by k square. So that is what the term is given in question, right? So what I'm going to do is, I'm going to take it as partial sum, right? So taking sum k equal to 1 to infinity tan inverse 2 by k square, it is same as taking limit n tends to infinity sum k equals 1 to n tan inverse k plus 1 minus tan inverse k minus 1. So we are going to put one by one values. We'll get limit n tends to infinity tan inverse 2 minus tan inverse 0 plus tan inverse 3 minus tan inverse 1. So and so, last two terms are tan inverse n minus tan inverse n minus 2 plus tan inverse n plus 1 minus tan inverse n minus 1. So what we can see is, just like previous examples, when we were cancelling the terms, we had only 2 terms left. But here we are left over with 4 terms. That is because here the terms left are tan inverse 0, tan inverse minus tan inverse 0, minus tan inverse 1, plus tan inverse n, and plus tan inverse n plus 1. That can be seen very clearly, because how did we get tan inverse 0? That was while we applied k equal to 1, and that was for k minus 1. Is there any other way we can obtain 0 from k plus 1? Because it should be of opposite sign. So here there is no way to obtain 0, which means there is no term of opposite sign for tan inverse 0. Similarly for tan inverse 1 also. Same issue we are having with tan inverse n and tan inverse n plus 1. So these 4 terms are left out after cancelling the terms which are of opposite signs. And what we get is limit n tends to infinity minus tan inverse 0 minus tan inverse 1 plus tan inverse n plus tan inverse n plus 1. So upon applying limit, we get minus tan inverse 0 minus tan inverse 1 plus tan inverse infinity plus tan inverse infinity. So from the usual way of taking values for tan inverse, we get it as 0 minus pi by 4. So for tan inverse 0, it is 0 itself. Tan inverse 1 is pi by 4. Tan inverse infinity, it is pi by 2. So upon calculation, we get it as 3 pi by 4, which is option 3. Right.
Ma'am, can you show question number 3 from the last?
Question number 3. I have not put question number. Do you remember what the content
Okay,
of the
last from the last 3.
last 1, 3?
Factorial is there.
Okay, this one with this one.
Yeah, this one.
Okay. I'll be sending the PPT after corrections to sir. So if you want to clarify once again in detail, you can check the PPT. If it's something that requires my clarification, you can ask.
Ma'am, this question can be done by like e to the power x series, and then if I multiply by x, then integrate and putting x is equal to -1, then also this series coming. No?
Yeah, there may be more than one way. I have followed some more detailed pattern so that even the weakest students get to know it. If you can do it in simpler way, yeah, that's much better. So it will not be much time consuming. So if you got another way of approaching it, it's fine. Good.
Hello, ma'am. Hello, sir. Ma'am, I am Dia Shah, and I am in my MSc second year. I am doing MSc from IIT Bhubaneswar and preparing for my NET exam. Ma'am, this is a really good revision for the sequence part, and the problems were really good, ma'am. Thank you.
Thank you, Dia.
Hello, ma'am.
Yes.
I'm Gayatri. I have studied in Miranda House College, Delhi. And it was a very nice class, and you have used the simple language, so it was very easy to understand the topics because of your clear explanations. And thank you so much for taking an amazing class, and thank you, Vinod sir, for conducting this class. So thank you.
Thank you, Gayatri. Yes.
Hello.
Yes.
Hello, ma'am. Hello, sir. Sorry, we have some power cut issue, so I'm not visible. I'm Nishita Pindarkar from Maharashtra. Ma'am, the session was really very good, and the way you explained all the concepts were just amazing. And thank you for the session.
Thank you, Nishita.
Hello, ma'am.
Hi.
Yes.
Hello. Yes, ma'am. I think so your session is very informative and very helpful. Teaching method is very systematic.
You didn't introduce yourself.
I am Sudha Kundu, and I preparing NET exam.
Okay.
Yes, ma'am. Thank you, ma'am.
So,
Thank you, sir.
so you're from West Bengal, am I right?
Yes, sir.
Okay.
Thank you, sir. Thank you, ma'am.
Okay. Thank you, Subra. Okay, others.
Hello, ma'am.
Hi.
Yeah.
I'm Shikha, and I'm a second year MSc student and studying from BIT Meshra, Jharkhand. Ma'am, the session was really nice. It was wonderful. The language you have used was really easy. And my problem is that I'm unable to manage my timing because in my college, my college used timing from 8 a.m. to 5:30 p.m. So I'm unable to find time for just studying and managing everything, college and the preparation. So could you please give some tips so that I can do better?
When it comes to time, especially when your college schedule is so tight, I don't know whether I'll be able to give some tip or not, because first thing that we need is time to do what we need to achieve, right? We need time for that. So no other option than that you have to spare time for clearing these exams for additional learning. So you'll have to, maybe you can prepare a timetable, like a schedule, like learning these topics like real analysis these many days, complex analysis these many days. It is just learning without any idea or without any aim, you will not reach anywhere. So first of all, you need to schedule yourself, prepare time limit for each papers, each areas, and then start preparing it. Right? Especially when you're short of time, it is very much required that you should schedule it like that. Because when you have plenty of time, yeah, you can do it any way you like. But when time is short, so you will have to make it little more clear, right? Yeah, it's okay.
Yeah, Shika, that is the point. Everyone has only 24 hours per day. So we have to make a wise plan to make effective use of time. Okay.
Yes, sir. Thank you, ma'am. Thank you, sir.
Yeah, thank you, Shika. Yes, others.
Hello, ma'am.
Hi.
Yeah.
Myself, Virupaksha. I am from Karnataka. I am studying MSc first year in the Central University of Karnataka.
Okay.
The session was very good, ma'am. The way of explanation was very nice, and we also easily understood. So this concept will be helpful for us upcoming exams, ma'am.
Yeah, thank you.
Okay. Thank you, ma'am. Thank you, sir.
Yeah, sure.
Yeah, thank you. Thank you, Virupaksha. Okay, dear friends, tomorrow we have a session on Jordan canonical forms, which is exclusively for MSc students preparing for NET and JRF. So be active in tomorrow's session also. Yeah, Dharmendra, you can speak now.
I am Dharmendra Singh from BARC Vizag Library as a technician. The session was very nice with nice problem and collection from IIT JAM, NET and NBHM. I want to ask about some book suggestion and problem book suggestion.
Actually, during the session of sequence itself, I have given 2 books. That is what I have prepared more. One is Bartle and Sherbet, Real Analysis book, and the other one is Malik and Arora, Real Analysis textbook. So in both these, in Bartle and Sherbet book, it is somewhat precise. More only important results are given, and when it comes to Malik and Arora, there are too many results. So as I've told, we have told that when these ratio test or root test fail, we are having few other tests also. All these tests are listed in Malik and Arora. So if you need a detailed description about all these tests, you can refer to that book. And for more problems and worked out examples also, you can take that book. Or in case you want a precise explanation, go for Bartle and Sherbet. So that's all.
Okay, thank you.
Yeah.
Thank you, Dharmendra. Others? Gopika?
Am I audible?
Yeah,
Yes, yes.
Hi, ma'am. I'm Gopika from Vidyapeetham College. Thank you.
Gopika, you're having some kind of network issue.
Yeah.
Your voice is not audible.
Voice is breaking.
Gopika, you please switch off your video and then speak. Then I think it will be clear.
It's audible.
Still, there is some kind of audio glitch.
Sorry, I have English.
Still, there is some kind of issue.
Yes. Okay. Gopika, you can use chat box. Any others?
Hi sir, hi ma'am. I'm Shakti Bhavdarni from Palakkad. This was my first class. I really liked it, ma'am. Your explanation is more easy to understand, ma'am. Thank you.
Okay.
Shakti, introduce yourself. Where are you studying in?
Government Arts College for Women Puliyagalam, Coimbatore. I am a final year student, BSc Maths.
Okay.
Okay. Thank you, Shakti.
Thank you, sir.
Anamika?
Yes, ma'am. Good evening. Can I audible?
Yeah, good evening. Yes, you're audible.
Hello, ma'am. Sir, I'm Anamika from Viswa College. This session was very nice, and I'm little late today, so it's. But the questions you discuss is really good, and I understand each of the problems very well. The questions you corrected is very different problems, so each part can be achieved much more knowledge about each part. So thank you, ma'am. And so, ma'am, can you mention that name of that books once more in chat box?
Yeah. I'll type it in the text.
Okay. Thank you, ma'am, and thank you, Vinod, sir, for this nice section.
Okay. Thank you, Anamika. Thank you.
Hi, ma'am.
Hi.
Yeah, Alina.
I am Alina Binu from St. Dominic's College, Kannur.
Okay.
Thank you for this nice section, ma'am. I was having some problems with the sequence and series section, but now I hope I can do more in this session and these questions. Thank you, ma'am, for this wonderful session.
Yeah, thank you.
Thank you, Alina. Any others? Okay, if any of you would like to express any comments, do it now. No need to be shy. Nandana? Nandana J. Verma. Yeah, you can. I have one more Nandana is there.
Sir,
Yes.
sir, ma'am, thank you for a wonderful for giving us a nice opportunity. And I'm a little bit sick, that's why I am not up. You can understand. I'm a
That's
little bit
okay.
sick.
PhD journey. I've just completed my coursework. I joined as research scholar in 2021. So it's just almost 1 year. My coursework is over. I'm currently looking on the problem on which I can do my research. It's yet to be fixed. So I'm working in graph theory, more dominantly on coloring, graph coloring. So the main area is to be fixed yet.